Jai Swaminarayan. I am Professor Urvish Mewada, HOD Electrical Department, Sri Swaminarayan Institute of Technology, Part Gandhinagar. Also, I am the subject matter of Industrial Instrumentation subject, which is in the 7th semester Electrical, and GTU subject code of the subject is 2170913. Students, we are discussing chapter number 2, and this is lecture number 5 for chapter number 2. Now, the topic is examples based on the strain gauge circuits. So, in previous lecture, we have discussed about the strain gauge circuits. Now, today we will see the example related to the strain gauge circuits and the rest of the theory like gauge factor and uh, the ballast circuit. Okay, so let us solve the example related to this strain gauge. Example number 1. So in this example, the statement of this example is a strain gauge having a resistance of 200 ohm. So this is the variable resistance on which we will apply the strain, and the gauge factor of this strain gauge is 2.5. So as we know that gauge factor is means sensitivity of any gauge is directly proportional to the gauge factor. So this is the gauge factor, and is connected in series with the this is ballast. This is mistake resistance of 400 ohm. This ballast resistance is a say compensating resistance for the strain gauge, and the total voltage across the combination is 24 volt. So input voltage for this strain gauge bridge circuit is 24 volt, and determine the change in the output voltage means V output or E output when a stress of 140 mega newton per meter square is applied. So whenever such kind of stress is applied, we need to find out the change in the output voltage. The modulus of elasticity means whenever the stress applied, our strain gauge will get expand. So due to its elasticity it will get expand, and then after whenever the stress is removed from the strain gauge, it will regain its original position. So that's why the modulus of the elasticity of this strain gauge material is 200 gn by means giganewton per meter square. So let us solve this example. So first of all, we are considering that when no stress is applied means this bridge is say balance, or we can say uh, um, no stress is applied means there is no change in the circuit. So let us check the output voltage of the circuit. As already we discussed that this means western bridge will show the output voltage even if the voltage is not applied. So let us check that whether it is correct or not. So E output is equal to Rg is the gauge resistance divided by Rb is the ballast resistance plus the gauge resistance into E input. So we have the value of Rg over here, it is 200 ohm. So put the value of Rg, and Rb is also given, it is 400 ohm. So this is the 400 ohm. So it is multiplied by the E output, or we can say output voltage. Here it is given. So the output voltage EB, or we can say ballast voltage. So 8 volt. So let us check the sensitivity of the gauge. So strain is the say directly proportional to the sensitivity, and the means the means output and the modulus of elasticity. So basically modulus of elasticity is stress over strain. So the stress applied is 140 mega newton per meter square. So put the value of S, and the value of E is 200 means giganewton per meter square. So this is the E. So from this we can find the strain. So that is the strain is 0.7 into 10 raised to minus 3. Now let us check the change in the resistance of the gauge whenever the strain is applied. So Rg was the original resistance, means gauge resistance whenever the stress is not applied. Now we apply the stress on this gauge, that means its resistance will become Rg to delta Rg. Now delta Rg is, we can say, directly proportional to the gauge factor, as I already explained you while I was explaining the data. So Gf into epsilon means epsilon means a strain into the Rg. So we have all the values of that we determine. Gf gauge factor is given, it is 2.5 over here, you can see. And the strain is that we get from this above expression, so 0.7 into 10 raised to minus 3. And Rg is the original resistance, that is 200 ohm. So delta Rg is 0.35 ohm. So voltage across the gauge when the stress is applied, let us check what will be the voltage across the gauge when the stress is applied. So this is the formula to determine the voltage is, this is the 200 plus 0.35. So 200 is say the resistance Rg, and what is the delta Rg? Delta Rg is 0.35, that we determine from this over here. So Rg plus delta Rg upon the ballast resistance is 400 ohm, so Rb plus Rg plus delta Rg. So it is multiplied with the 24, means input voltage. So the voltage that we get when we apply the stress is 8.0093. Now let us check the change in the voltage. So that will be the difference of say whenever the stress applied, means voltage across the bridge or galvanometer shows the deflection whenever the stress is applied. So this is the output voltage, and this is the input voltage, means that we get whenever the stress is not applied. So this is the voltage at which we apply the stress, and this is the voltage at which we doesn't apply the stress. So this is the difference, 0.00932 volt. So from that we can say 9.327 millivolt. So whenever we apply the stress, the gauge will show the deflection, and this much amount of voltage will change when we apply the stress on the strain gauge. So this is how we can calculate the examples related to the strain gauge. Now let us check the example number 2. So the statement of the example number 2 is, a strain gauge with a gauge factor is of 2 is fastened to a metallic member, means it is sticked or pasted on the metallic member subject to a stress on which we are applying the stress, means the metallic member on which we are applying the stress, on which we have connected or pasted, means we already discussed that some of the strain gauge we can paste on the surface of the metal with the help of adhesives. So this is the strain gauge which is pasted on the surface of the metal. So subjected to a stress, say 1000 kg per centimeter square. So this is the stress is to be given. The modulus of elasticity of the metal is 2 into 10 raised to 6 kg per centimeter square. So this is E, capital E. And calculate the percentage change in the resistance of the strain gauge. So we will check the percentage change, means whenever the stress is applied to the not applied, ratio is the percentage change in the resistance of the strain gauge. So what is the value of Poisson's ratio? So we need to determine the value of Poisson's ratio, V, small v. So here the data given is gauge factor is 2, then the S means stress, that is that we applied is S is 1000 in kg per meter square, and E is the modulus of elasticity, which is given 2 into 10 raised to 6 kg per centimeter square. So to find out, first of all, delta r by r, and second term is v. So let us solve one by one. So we have the equation of strain, or we can say modulus of elasticity is equal to stress over strain. So we need to find out the strain. So let us put strain as a subject. So S is the stress over the modulus of elasticity. So stress is 1000 into 1000 divided by 2 into 10 raised to 6. So 2 into 2 into 10 raised to 6. So this is the value of E. So from this we can determine the epsilon, that is 500 into 10 raised to minus 6, or 500 micro strain. So this is the strain we are going to apply on the strain gauge. So whenever the stress is applied on the strain gauge, so its resistance will be changed. So that's why the resistance in the change delta r is proportional to gauge factor to the stress into sorry strain into the original resistance. So we have the value of gauge factor that is given over here. See, you can see over here 2 is the gauge factor value. Now ए E मतलब epsilon is the strain that we means or a gauge will have the see the strain whenever the stress or strain is applied. So 500 into 10 raised to minus 6 and delta r sorry we put r over here, so we can determine delta r by r. So 2 into 500 into 10 raised to minus 6 will become 0.001. So percentage delta r by r is 0.1%. So this is the ratio of change in the resistance to the resistance is 0.1%. So whenever the 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 object, or the we can say the substance which is on the stress having say the stress which is applied is 100 sorry 1000 kg per centimeter square, at that time our gauge will show the percentage change in the resistance is 0.1%. So from this we can determine the value of the see the Poisson's ratio. So we have the equation of gauge factor is equal to 1 plus 2v, where in this equation gf is the gauge factor of the gauge and v is the Poisson's ratio. So we have all the values of gf. So gf is 2 minus 1 divided by 2, so v is 0.5. So the Poisson's ratio is 0.5. So from this we can say that the when the membrane is subject to the stress, say having 1000 1000, see over here the stress is given 1000 kg per centimeter square. At that time your gauge will show the deflection, say the change in the resistance is 0.1%, and at that time the Poisson's ratio indicates that it is 0.5. So this is from this you can assume that this gauge is means sensitivity of this gauge. So this is how we can use this strain gauge as a transducer to check the stress over strain means stress applied to the particular object and according to the object this is the percentage change in the resistance and the Poisson's ratio offered by the gauge. Now let us check the example number 3. So let us discuss the example number 3. So this is we can say strain gauge which is connected on the cantilever beam. Cantilever beam means one vertical pole we have, and on the top of the pole one horizontal part is connected in that part is called hinge support, or we can say one portion is fixed with the pole, and second portion of the pole or second end of the gauge is floating on the air. So at that point, the point which is on the floating on the air, on which we are applying the stress, and we will check the gauge factor of the means strain gauge. So a strain gauge having a resistance of 120 ohm. So strain gauge resistance R is 120 ohm, and which is mounted on the steel cantilever. Cantilever means, assume that we have one pole which is fixed on the surface, means vertically, and on the top of the pole we have connected one horizontal, gauge, means having two ends. So first end which is fixed on the pole, and second one is floating in the air. Assume that structure. So steel cantilever beam at a distance of 0.15 meter. So 0.15 meter basically, uh, uh, the we can say is the distance from the pole, from the feet end, means from the bottom. An unknown force is applied at the free end, means the free end which I was talked about. So this is suppose this is the pole, sorry, this is the gauge which is connected on this pole, suppose. So this is called the free end. So free end produces a deflection of 12.7 mm. So change in the means original position to change in the position is 12.7 mm. So that is x is equal to 12.7 mm of the free end. The change in the gauge resistance is found to be 0.152 whenever the stress is applied on the strain gauge. So the resistance of the gauge will change, so that will change from 120 to 0.152 ohms. The beam is 0.25 meter long, so length of the beam is 0.25 meter, uh, with a width of 20 mm. So for the beam having the width, it is 20 mm, and a depth of 3 mm. So depth of 3 mm is the we can say the width, sorry, the length. The Young's modulus for the steel is 200 giganewton per meter square. So calculate the gauge factor. So Young's modulus is also given E, that is 20 giganewton per meter square. So it is over here. So calculate the gauge factor GF. Now uh, let us discuss the data given. So B is the width that is given 20 mm. E is the modulus of elasticity. X is the change in the distance after applying the stress. L is the length of the pole. D is the depth of the pole. R is the original resistance, and delta R is the change in the resistance after applying the stress. So let us calculate the moment of inertia first. So moment of inertia I is equal to uh, 1 by 12 BD cube, where B is the say width of the pole, and D is the depth of the pole. So 1 by 12 into 20 into 10 raised to 3, that is given, and 3 into 10 raised to minus 3 cube, because we are finding the moment of inertia. So I is equal to 4.5 into 10 raised to minus 10 meter square. So this is the printing mistake, inertia is in meter square. uh, then after we have the equation for Young's modulus. E is equal to FL cube divided by 3xi. So let us put x as a subject. So after putting x as a subject, so means we have the change in the distance. Equation is x is equal to FL cube divided by 3 into E into I, where E is the Young's modulus, I is the inertia, L is the say length of the pole, or we can say, sorry, beam, and X is the distance which is changed after applying the stress. So let us find out F from this. So make F as a subject. So this will become 3E uh, Ix divided by L cube. So we have all the values. E we have 20 into 10 raised to 9, that is given. E is the 20 into 10 raised to 9 it is given, and for the I is the 4.5 into 10 raised to minus 11, and X is the 12.7 mm or 12.7 into 10 raised to minus 3, means after applying the stress, this is the change in the position of the strain gauge. And the L means length of the pole is 0.25 meter cube, so it is means we can say L cube, so put the value of L over here, so 0.25 cube. So F is from this equation, after placing the values, it is 22 Newton. So for this pole, the force applied is for this amount of change in the position, we can say the force which is exerted on the means free point or free portion, or say the point at which the point which is on the floating on the air. So the after applying the stress, the force can be means force will be 22 Newton. So the bending moment of at point 15 meter from the free end. So this is the point at which we need to check the bending moment. Let us check at this point what happened. So this is the uh, this is the gauge which is mounted on a steel cantilever beam at a distance of 0.15. So suppose this is the steel plate on which 0.15 meter at 0.15 meter the strain gauge is pasted or mounted on the beam, sorry, on the steel cantilever. So the equation is m into f into x. So we have the value of f, that is force that we found out from the previous slide. So f and x is the change in the sorry, x is the distance at which mm, uh, the uh, the strain gauge is pasted or strain gauge is mounted on the steel cantilever. So from this we can determine the value of bending moment m, so that is 3.3 Newton meter. So the stress at point 15 meter from free end is stress equation S is equal to bending moment divided by moment of inertia into T by 2. So the equation, from this equation we have all the values. We have the value of m, that is 3.3 Newton 3.3 Newton meter, and I we have the value of moment of inertia 4.5 into 10 raised to minus 11. We have the value of t, that is 0.003 divided by 2. So after placing all the values, we can determine the value of stress, that is 110 mega Newton per meter square. Now we have the value of we have the equation of Young's modulus. E is the delta S over epsilon. So change in the stress divided by or we can say S by E. So this is the means stress which we are applying on the beam. So uh, at 0.15 meter, so this is S by E. So 110 into 10 raised to minus 6 is the value of S stress, and E is the 200 into 10 raised to 9. So from that the strain is 0.55 into 10 raised to minus 3. Now the gauge factor equation, we have change in the resistance to the original resistance divided by change in length to the original length. So V is equal to delta R by R divided by delta L by L. So this will become delta L by L is the epsilon, or we can say strain. So delta R by R divided by epsilon. So the resistance changed after applying the stress is 0.152, and the original resistance is 120 ohm, divided by the strain that we get from this, so 0.55 into 10 raised to minus 3. So after solving this, we will get the gauge factor or Poisson's ratio is 2.3030. So let us solve another example related to this. So Example number 4, for example number 4, the data which is given. So for the example number 4, the statement of the example number 4 is a strain gauge is bonded uh, to a beam 0.1 meter long. So on the beam the strain gauge is bonded, say the length is 0.1 meter long and has the cross sectional area is 4 centimeter square. Young's modulus for steel is 207 gn by meter square, gn per meter square, and the strain gauge has an unstrained resistance of 240 ohm and a gauge factor is 2.2, which is given. So when a load is applied, so whenever the force is applied, the resistance of the gauge changes by 0.013 ohm. Calculate the change in the length of the steel beam whenever the stress applied, the amount of force applied to the beam whenever the force or stress applied, find out the length of the beam. So L is a point at which the gauge is bonded, so that is 0.1 meter. A is the cross sectional area, that is 4 centimeter square. E is the modulus of elasticity, Young's modulus, that is 207 gn per meter square. R is the resistance when the stress is not applied, so that is 240 ohm. And GF, gauge factor, which is given 2.2, and change in the resistance is 0.013 ohm. So these are the data given. Let us find out. First is change in the length delta L of the steel beam, and the second is the force. So step 1, find the to find the change in the length of the steel. So first of all, we have the equation of gauge factor, that is delta R by R to the delta L by L. So from this we can make subject delta L, and we can put other terms like this. So delta R by R into L divided by GF. So we have the value of delta R, that is 0.1013, and the original resistance is 240 ohm, into L, at which we place our means strain gauge on the we can say surface of the object. So this is the point 1 L. Now the delta L, after putting this values, delta L is 2.462 micrometer. So this is the change in the length when we apply the stress on the object. So step 2, to find out the force. So we have the equation of modulus of elasticity is stress over strain. So let us make subject S. So we have the value of E, that is 207 into 10 raised to 9, and again epsilon is the change in length to the original length. We have this two also. So S is equal to 207 into 10 raised to 9, and change in length that we found out from this, so 2.462. So put the value over here, and L is the length, means original length at which we placed our strain gauge, so that is 0.1. So S is equal to 5.092 into 10 raised to 6 Newton per meter square. See over here, L is the gauge is bonded to a beam 0.1 meter long. So this is the length L, so that is 0.1. So from this, S is 5.092 into 10 raised to 6 Newton per meter square. So force is equal to the stress into the cross section area. So we have the S is 5.092 into 10 raised to 6 into a cross section area is 4 meter square. Over here the 4 centimeter square it is given. So 4 into 10 raised to minus 4. So the force which we get from this is 2.038 into 10 raised to 3 Newton, or we can write this 2.038 kilonewton. So this is how, when we apply a stress on this particular object, so this will be the force when the length of the means object will change from original length to the means change in length by applying this much amount of stress. And this can be like calculated with the help of the such equations of means the with the help of the different equations of the strain gauge. Now let us discuss the example number 5. So the strain gauge having a resistance 100 ohm, that is the original resistance, and the gauge factor is 2 is connected in series with a ballast resistance. So again, this is our bridge circuit, and ballast is the compensating say resistance for the strain gauge of 100 ohm. So this is the again, both resistance are same, means the gauge resistance and the ballast resistance across a 12 volt supply. So 12 volt supply is connected to the bridge circuit. Calculate the difference between the output voltage with no stress applied and a stress of 140 meganewton per meter square. Means we need to calculate over here the difference between the output voltage whenever the stress applied and whenever the stress is not applied. The applied stress is 140 mn per meter square. The modulus of elasticity is which is given is 20 gn per meter square. So let us find out the step number one. To find out the voltage and strain when no stress is applied, the voltage across the gauges V output is equal to V input into the gauge resistance to the total resistance of the circuit. So V input we have, that is 12, Rg is the gauge resistance, that is 100, and Rb is the ballast resistance, which is again 100, and plus Rg is 100. So by solving this, we will get V output is 6 volt. So the strain is epsilon is equal to S by E. So we have the value of S, that is given 140 mn per meter square, and modulus of elasticity is also given, that is 200 into 10 raised to 9. So from this we can determine the strain, that is 0.7 into 10 raised to minus 3. Now to find out the delta R, so delta R is equal to R into GF into epsilon. We have the value of GF, epsilon and R, so we can find out the delta R. So the original resistance is 100, GF is 2, and the strain that we get from this is 0.7 into 10 raised to minus 3. So delta R is equal to 0.014 ohm. So the step number 3 is to find out the change in the voltage. So voltage across gauge on the applying the stress is V output is equal to the gauge resistance to the change in resistance. So 100 was is the original resistance, and this is the resistance will change after applying the stress. So then after it is again Rg plus Rb plus delta R. So this is the values of the all resistances into the input voltage 12. So output voltage is 6.00419. So change in the voltage is V input to the V output, means whenever the stress is not applied and whenever the stress is applied. So 6 minus 6.00419 is 0.41 millivolt. So from this we can say that we can conclude that whenever we apply a stress on this particular gauge strain gauge, this much amount of voltage will change, means this much amount of voltage difference will get whenever the stress is applied and whenever the stress is not applied. So thank you very much, student. If you have any doubt or any query related to this topic, we can solve our doubt in the doubt solving session. Just just pay your attention on such type of example. Examples are repeatedly asked in the GTU exam. So we included all the examples related to this chapter or all the theories. So if you have any further doubt, so feel free to call me anytime. So thank you very much, student. Thank you very much all. Jai Swaminarayan. And this is the last topic of our chapter number 2. So in next lecture we will discuss the chapter number 3. Thank you very much all. Thank you, students. Jai Swaminarayan.